Welcome to our lecture on graphical displays. So this is a graphical display made by a previous student on a project about hospital charges across the U.S. It was made in R, and the bubbles indicate, the size indicates the average cost for that city for heart attack codes. So I wanted to show you some of the neat graphical displays that can be made using R. But first of all, we can describe data sets numerically, or we can describe them graphically, and/or. And the choice of graphical display depends on the type of data. We're going to explore several types of graphical displays this semester. First of all, the box plot. I know you've seen this previously, but let's review it again. So this is a box plot of single-family homes, a quantitative data set. It displays quantitative data. Box plots work for small to large data sets. And it's a plot of the 5-number summary. So if you remember from your previous stats course, this bottom whisker goes down to the minimum observation in the data set. The bottom of the box is the first quartile. The line that divides the box is second quartile, otherwise known as the median. The top of the box is Q3. And the top of the top whisker would be the max, except lots of software programs plot outliers separately if there are any. R does that as well as Excel. All right, so we're going to use an example data set. These are lake levels for Lake Murray. This is a lake in the Midlands region of South Carolina. And the USGS tracks in real time lake levels. So this is lake level data from 2007 through 2015. It's hourly lake levels for Lake Murray in South Carolina. And I'm telling you where I downloaded the data from so you could look at some of the data yourself if you ever want to use it. So lake levels affect tourism. When the lake is low, it becomes unsafe to boat, water ski, wakeboard, tube, etc. Plus the lake is drawn down in winter, so it's colder. So each year the lake is drawn down in the winter months, roughly September through March, and allowed to rise in the summer months, April through August. When the lake levels are low, it affects tourism. So we're going to go to R and call in this data set and talk about how I got the code for the box plot. So I've got R pulled up here, and first we're going to call in our data set. So I'm going to name an object, just like we did in the R video, and I'm going to use my definition symbol, the less than dash sign. And usually if I have two words, I'll make the second word start with a capital letter just so it's easier for me to see. We don't want to leave any spaces in our object names. So lake level is read.csv. When you download the lake level data set, you will notice that instead of a .txt file, it's a .csv. This is a special type of Excel spreadsheet that kind of takes out all the behind the scenes HTML and stuff, kind of strips it down so that it can speak to many, many languages. All right, so read.csv, since we have a CSV file. And then the rest of the code is the same as we've done before. File.choose, header equals true. And I'm going to search for this data set in my downloads folder, which is where I put mine, and here it is. So let's see how big this data set is. I'm going to use the dim lake level call. It is 67,810 rows with 9 columns. Clearly, I don't want to look at the whole data set. It will just jam up my whole screen, and I won't even be able to scroll up and see the column names. So what's my trick for looking at the names of my variables? Well, I can just type lake level, so the name of my data set, and I want to look at the first 5 rows and all columns. So I'll hit enter, and now I can see what my columns are. Some agency code, a site number code, the month, the day, the year, the time. This one may or may not have been labeled. We'll look at the Excel spreadsheet in just a second. The level, that's the thing that we're looking out for, and then the season. All right, now I want to know what is in the season column. So if I use my summary trick, first I'm going to attach the data set so I can just refer to my columns by their column names. And then I can use my summary command for the season column, and it'll tell me that I have 28,869 observations that are in season and 38,941 observations that are out of season. So that's a trick that you can find out what all levels of a categorical variable that you have. Similarly, I could do summary of X. Remember, I used my scroll up arrow to get my old code, and then I just edited it for speed and hit enter, and I can see that there's just AM and PM. And of course, you probably knew that was the case, but this is the way that you can tell how many levels of a categorical variable you have. All right, and if you do summary of a column that R thinks is quantitative, like year, then it's going to give you the 5-number summary and the mean. So it looks a little bit different for categorical versus quantitative variables. All right, now I promised you that we were going to look at this data set. So let me go to my downloads, and I'm going to pull up this data set. Okay, so this is what it looks like in Excel when I pull it up, my CSV file. And you can see that the column for AM and PM was left blank. So what R did was it gave it a name. It gave it the name capital X. So sometimes the way that your variables are named in your Excel spreadsheet will look different in R. Like if there was a space here like year, if it was named year month, and there was a space in between year and month, R would put those words together and separate them by a period. So I always, in R, take a look at like the first 5 rows so I can see what my column names are in R, so I can refer to them in a way that R will understand. All right, now real quick, before we leave the Excel spreadsheet, I want to show you a little tip, because you're going to be working with bigger data sets. And a lot of you are going to be tempted to try to scroll down to the bottom and look at your data that way. I am going to encourage you not to do that. It is very, very tedious. Start using your shortcut keys. If I want to highlight this whole data set, for instance, instead of scrolling and doing this number and then scrolling down and waiting and waiting and waiting and waiting and waiting, I can simply click in this top left cell. I'm hitting Control and Shift. On a Mac, it would be Command and Shift, and then the down arrow will get me all the way to the bottom. And then if I hit the right arrow a couple times, it will take me all the way to the right. And so now you can see that I've highlighted my whole Excel spreadsheet. So make sure that you're using little tricks like that if you're having to manipulate the data inside of Excel, because when you have a bigger data set, scrolling is not going to be your friend, and eyeballing is not going to be your friend. All right, so back to R. All right, so we want to create a box plot of the lake levels. All right, so I'm going to use the box plot command, and I've already attached my data set, so I can just refer to the lake level column of data as level. So I'm going to call it with a capital L the same way it's listed in there, and I've got a box plot. Pretty cool. Now you can see that this data set has lots of low-lying outliers. Those are lots of dots smushed together, and that's why it looks like another line past that bottom whisker, but that's really just a bunch of outliers. All right, so the next thing we want to do is learn to create side-by-side box plots, because that's what we're doing in our lecture, all right, because that's one thing that box plots are really good for. So if I want to create side-by-side box plots of the level variable separated by season, then I'm going to tell it to give me a box plot of level, and I'm going to use the tilde symbol, which is Shift and the top left key on my keyboard. And that means by. So lake level by season. And if I do that, it gives me a box plot of the lake level separated out by in season and out of season. Okay, so now we're cooking. But now we want to pretty this thing up. We don't have any title. We don't have a label on our y-axis. My box plot names are the way that I coded it in Excel, so they don't have spaces, so they're not prettied up. So we want to learn how to add labels, maybe even change the order of our box plots. All right, so first, I'm going to scroll up in my R console. When you're in the picture window, you have to click back in the editor window in order to edit your code. So I'm going to use my scroll up arrow to get to my last line of code. I'm going to backspace, and I'm going to add another function in here, another argument in my function called names. And I'm going to tell it to concatenate two words. So names equals concatenate, and then in quotes, I'm going to say in season, and that'll be the name of my first box plot, and my next one's going to be out of season. End my parenthesis for that, and you can see that now it's named it with spaces. Who knows? Maybe I want to call it summer and winter. I could do that if I wanted. And you can see that it changes it on the box plot. Very good. All right, so now let's say that I want to switch the order of my boxes. So mine, I only have two boxes on my box plot, on my side-by-side box plot display. So what I can do is I can scroll up to edit my code, add a comma to add another argument to my box plot function, and I'm going to use the at command. So I'm going to say at equals concatenate, and then I'm going to tell it to put the second box plot first, comma, the first box plot. And what it's going to do is it's going to take these two box plots and it's going to make the winter one on the left and the summer one on the right. It's going to take the second one and put it first and the first one and put it second. So I'm going to hit enter, and you can see that that's what that command does. All right, so let's say that we want to add a Y label. So I'm going to scroll up, I'm going to arrow back, and I'm going to say ylab equals, and I'm going to put it in quotes because it's words, and I'm just going to say level and give it the units in feet, and it added it. Okay, now I want to add a title. So I could scroll up to edit my code, put a comma in, and say main equals whatever your title is. I gave you one example in the lecture notes. I'm just going to call it my title right now so you can see that it pops it up there. Very good. And if you want to stretch out your graphic to make it more, rectangular to fit better in your document wherever you're putting this, you can resize it just by grabbing the edges. So I just wanted to point that out to you. All right. Now sometimes don't forget, if you're working with your editor window and it's taking up the whole space, you won't see your graphics window pop up when you do it. Just make sure you always know that you can minimize that and find your graphics window. All right. Now sometimes when you right click and copy this as a bitmap to maybe paste it in a Word document, like what you're going to do with your first project for me, the titles and everything need to be a little bit bigger. So what you can do is add the CEX arguments. So if I do cex.lab equals 1.25, what it does is it makes my label size, font size, a little bit bigger. If I do cex.main, usually I do like a 1.5 or 1.75 or 2 for my titles. You can see that it makes the title bigger. Okay, so, and then if I wanted to add an X label, I could do xlab equals season, and you can see that it adds that to the graphic as well. All right, and then I've got in the our help page in your notes a way that you can change the margin size so that you could leave like a little more or less room for this y-axis label, a little less room on the bottom so there's not so much wasted space, but I'll let you read about that. That's the basics of how you create a box plot in R. Okay, so you've got the code that I used to create our side-by-side box plots in your notes. Right here it is. And here is that par-mar call. This is telling it to change the margins to 5, 5, 4, and 2. So that goes in counterclockwise order, and you can play around with them to get the margin size that you want on each side of your graphical display. So the code in your notes is just what I came up with the day that I wrote these notes. I've given it an adequate title, Lake Murray elevation, the dates. I put the elevation as the Y label. I put my units, feet. Notice the capitalization where it needs to be in my title. Pretty much everything is capitalized. I capitalized the name of my X and Y labels. I gave it units. Make sure that things are well labeled when you submit your graphical display to me. Give it some thought. Think about the order that you want your boxes in. Think about the way you want your title to read. It should be short and succinct enough to get the message across, but not so cluttered that it makes your graphical display look cluttered. All right, so now histograms. Histograms also work for quantitative data sets. In a histogram, the bins touch, and the number of bins can distort the features of the shape of the distribution. So sometimes you have to play around with the default histogram that comes out of a statistical software program such as R. So I did a histogram of these lake levels, and now you can see more features of the shape of the data, right? You can really see the left skew and those observations that the box plot was denoting as outliers, those low lake levels that don't happen very often. So inside the histogram function, inside R, I told it to make a histogram of my column called level. I gave it an X label, which I said was elevation in feet, and you can see that it applied it down here. I gave it a main title. You can see what that is right there. And then I just changed my label size to 1.25. And it was formatted fairly well for this slide, and so I left it alone after that. But there are all sorts of ways that you can change the arguments of that function too to customize your graphical display. Notice that a box plot displays the same data as a histogram, but the histogram shows a lot more details about the shape. A box plot, for instance, can't show two modes in your data. It can't show bimodality. All right, so some shapes of distributions that we want to keep in mind are skewed left, symmetric, and skewed right. That's on the top row up here. Symmetric, obviously it has a line of symmetry, a place where if you fold the graphic, the left and right sides are mirror images of each other. Skewed left is kind of like the left side of a symmetric unimodal bell-shaped distribution, and skewed right you can think of as kind of like the right side of a bell-shaped distribution. Skewed left has a long left tail, and skewed right has a long right tail. Bimodal is when you have two bumps in the data, maybe two populations or something else that's making it have two modes. Multimodal is when you have any more than two modes. Here we have three modes, so we're calling it multimodal. And symmetric, there is a line of symmetry where the left side looks like the right side. This one's bimodal and skewed right. Usually if you say bimodal, you just talk about where the large mode is and where the smaller mode is instead of saying skewed right or skewed left, but this came out of a textbook. It's fine for our purposes. Here, skewed left with outliers, symmetric with outliers, and skewed right with outliers. So those are some of the basic shapes that we'll be mentioning this semester, just like you learned last semester. All right, so a line graph is another type of graphic that we're going to be studying. It displays quantitative data changing over time. Time should always go on the horizontal axis and the variable should go on the vertical axis. And you can use different lines to denote separate categories or groups. So this is a data set that I downloaded from the Bureau of Labor Statistics, bls.gov, and it is unemployment rates separated by different degree categories. So this top line, the black line, is for less than high school. The second dotted red line is those who have a high school diploma. The third line, the green one, is some college, and the bottom one is bachelor's degree or higher. So why did I use this as an example of a line graph with separate lines for separate categories? Because it sends a good message. Notice that the overall pattern on this line graph is that the unemployment rate went up during the Great Recession around 2009, 2010, and it generally goes down after that for all groups. However, the lower education level, the higher the unemployment. So I just thought that was a nice little example to show a line graph with several different lines on it. Now notice here that not only did I separate the lines by color, I also thought about those who might be colorblind. And I also made the lines different according to the type of dots, the type of dotted line for the line. Lots of times you're going to have a legend up here, like in the top right corner, that will say less than high school, and it'll have a black solid line denoting that. High school, it'll have the color red and that sort of dot. Having the different types of lines helps out those who are colorblind. Beware of plotting different scales on a line graph. You will see this in the mainstream and scientific media sometimes. I would be very wary of it. It's very easy to distort messages like this. I would just do separate line graphs. That's my recommendation. Here we have on the left dollars per month and on the right minutes per call. And I don't know if, I think it just clutters the graph and distorts the message. So I would recommend keeping them separate if I were you. All right, a bar graph is for categorical data. It can be horizontal or vertical, and it can display the parts of a whole, or it can display separate values. If you have nominal data, it's usually nice to put the bars in ascending or descending order. But if you have ordinal data and there is a natural ordering to those categories, then it's usually nice to put the bars in the order of the categories. So I've got an example here, total U.S. government tax revenue as a percentage of the gross domestic product for 8 countries who are part of the Organization for Economic Cooperation and Development. Now, what kind of variable is this? First of all, how do I know to do a bar graph for this? Why is it not a histogram? Why is it not some other type of graphical display? Well, here we have categories, and we have one number for each category. Canada only has one number in my data set, right? It's the total government tax revenue as a percentage of the gross domestic product. So each category has one number. So that means it's a bar plot or a bar graph, whichever one you want to call it. Now, the categories here don't have a natural ordering, right? So this is not an ordinal random variable. This is just nominal, these countries. So it's not like it would make sense to put them in order in terms of their categories. I wanted to show you another example of the same bar chart that could make it a little bit better. Notice here, I turned it on its side just to show you that you can do it, the bars vertically or the bars horizontally. And what did I do? I ordered the bars from the top, from the greatest to the least. Now it's very clear, making comparisons, which ones are higher than others. For instance, on this one, it's hard to see the difference between Switzerland and the US and which one's higher. But here, it's much more clear. Here you can really see the ordering and which ones are bigger than the other ones. And notice it didn't make sense to order the categories, so I ordered the bars from ascending or descending order. There are many variations of bar graphs. Here is a stacked bar chart, otherwise known as segmented. Again, it can be vertical or horizontal. Here it can display 2 categorical variables. Here, belief in God and generation. Notice that there's still a space between the major categories, the generation, millennials, Gen Xers, baby boomers, and the silent generation. But when you stack the bars for the other variable, those do touch. A side-by-side bar chart is very similar to stacked, except that when you have these subcategories, you put them beside each other rather than extending the bar out and stacking it. Again, between these major categories, there is a space, but the subcategories do touch. And a back-to-back bar chart. So these are typically horizontal, like the way you'll see it here. There are 3 categorical variables on this one: race, generation, and approval. And notice that to be back-to-back, one of the variables has only 2 categories. So that's approve and disapprove, separated here. All right, a pie chart is, or a pie graph is, I'm sure, something you're all familiar with. This also displays categorical data. It's used when you have all the parts of a whole. So it's not good when there are too many categories, like more than 3 to 5, I would say, is too many. And please don't ever make it 3D or tilted. We recommend against that. All right, so notice that all the slices of the pie add up to 100%. So that's all there is to a pie graph or a pie chart. Notice that pie charts are not good for comparisons. Here is an actual set of pie charts that I got from a CDC brief on categories for death for different age groups. There are lots of things that they did well in this graphical display, like the color coding being the same from age group to age group, but having the legends separate from the pies themselves, and then on top of that, trying to compare different pies to each other makes it very hard for us to make comparisons. Our eyes have a very difficult time changing an angle into a number and then comparing it to the size of another angle. All right, a scatter plot is for quantitative data again, but it's when you're comparing 2 quantitative variables. So each point is a pairing, x and a y coordinate. It can show linear, curvilinear, or no relationships. And if they go what we call uphill, we call it a positive relationship, as is displayed on this example. And if it goes downhill, then it's a negative relationship. So here we have income against years of education. One would hope that's a positive relationship, that as you have more education, you should get more income. And it does look like it works out that way. So that's a scatter plot. We'll be talking about those a lot more when we get to regression. But that's for 2 quantitative variables. So make sure you make a note of that because it doesn't look like I wrote it on here. So depicts 2 potentially related variables, and these are quantitative variables. So make sure you write that in there. Sorry for the sloppy handwriting, that says quantitative. All right, things to avoid when you're making graphical displays. Please avoid these 3D displays. I know it used to be the default in Excel. Excel's gotten a lot better these days, but make sure that you do avoid any 3D or tilting effects in graphical displays. Again, it distorts the areas and makes it more difficult for us to make valid comparisons with our eyes. We fixed this one up. We've ordered the colors from warmer to cooler because this was about survey text. Normally colors are nominal variables, but here it was about this warm to cooler spectrum. So it did have a natural ordering to it, but normally that is not the case. We gave it a good title. We took the 3D out of it, and now it makes a lot more sense and looks a lot better. It's easier for us to make comparisons and get information from the graph. Avoid violations of the area principle. Those of you who are from around here, we have a kind of infamous intersection called Malfunction Junction. And it's about to be redone over the next couple years. And so the South Carolina Department of Transportation, SCDOT, has created this website to explain and keep the public informed about what's going on. So they've got this graphical display on their website explaining this project, and you can see that they've used people instead of bars on their bar chart. Now normally a bar chart is great, okay? They're treating this time kind of like a categorical variable because it's not equally spaced, so I applaud them for that. Otherwise, they'd have to make a line chart that was, much, much longer to go out to 2040 because there's 10 years between these, 4 years between these, and then almost 30 years between these 2 categories. But the problem is that when they, so they want us just to compare the heights of these, what we should call bars, okay, to get the population. So we could think about the projected population increase in 2040. But because they use pictures instead of a bar, and they didn't want to distort the picture and make this guy really tall and skinny, they also made these taller ones wider. And what that does is it violates something that we call the area principle. If, for instance, in a bar chart, what that is you should only vary the height of the bars. You should not vary the width. Otherwise, that area grows at a higher rate than does the actual number that they're trying to show. And our eyes take in that total area and think of it as a much larger increase than it actually is. All right, so a basic roadmap to designing effective graphics is determine your message. Select the most effective format to display your message. Tables display individual values to be looked up and compared. Graphs, the messages in the shape of the values. Design the data to show the most important parts. Look up Tufte's rules. That's a really good little set of rules. Make the data clear and straightforward. Remove all components that aren't necessary, so don't clutter your graph. And highlight the most important parts and mute the supporting elements. Encourage the eye to compare the data. Some final notes about graphical displays is don't forget a good but succinct title. Add the sample size if it's not immediately apparent, and don't forget units.